Page 1 of Chapter 16, Complex Numbers. Complex numbers can be expressed as 2D vectors. In this chapter, we're going to talk or introduce Euler's beautiful equation, which is e to the I pi equals -1. It might also be expressed as e to the I pi plus 1 equals 0. And it's called the beautiful equation because it has the three great math constants in it, and they're all related to each other, e, pi, and I. The more general Euler's result links e with the trig function. So, for example, we have e to the I theta instead of e to the I pi, and then e to the I theta can be expanded into cosine theta plus I sine theta. And if you think back to our investigation, you will be reminded of how that can be demonstrated. And theta, in this case, is a real number. So it becomes imaginary because we multiply it times I. In the complex plane, also called the Argand plane, the x-axis represents the real part and the y-axis represents the imaginary part of a complex number. A 2D vector can represent a complex number in an Argand diagram where the x component is the real part and the y component is the imaginary part. Addition, subtraction, and scalar multiplication work on complex numbers as they do on vectors. Okay, and so if z is the vector OP, its conjugate z conjugate is a reflection of OP in the x-axis. So let me draw a picture of that. So if this is the Argand plane, and you have OP here, then the conjugate of OP would be a reflection of OP in the x-axis. So it would be down here. Okay, so this would be z conjugate, and the top original vector would be z. Okay, so the first thing we're going to do is we're going to look at, on an Argand diagram, illustrate the following complex numbers. So I am going to draw a sketch of the Argand plane here, and let's draw 2, 3, 4, 5, 6 in that direction, 1, 2, 3, 4, 5, 6 in that direction, 1, 2, 3, 4, 5, 6 in that direction, 1, 2, 3, 4, 5, 6 in that direction. So first let's do the vector z1 equals 5, and that is a vector which only has a real part. And so remember, the real part is in that direction and the imaginary part is in that direction. So if it's 5 units in the real direction, then it would be 1, 2, 3, 4, 5. It would be that vector right there, right? What about the vector -6 minus 2i? -6 minus 2i would be 6 to the left, because -6, and then -2 down because of -2i. Remember, I values go up and down. So that would be about there. And there's the vector right there. Okay. And last of all, 2 minus I. 2 minus I would be 2 to the right and 1 down, which would be right there. So, okay, that was 2 minus I. So we've drawn the three vectors on this Argand diagram. Okay, number 3. Suppose that z1 equals 4 minus I and z2 equals 2 plus 3i. Find using both algebra and vectors. So let's use algebra first. So z1 plus 1, that would be 4 minus I plus 1. And we have two real parts here, 4 and 1, so we'll add those together. We get 5 minus I, which is the result. What about c? z2, which would be 2 plus 3i. And then we're going to do scalar multiplication of 1/2 times z1, which would be 1/2 times 4 minus I, which would be 2 minus 0.5i. And then we'll just add those two together. So we'll get 4 plus 2.5i. And let's see, we could find these also by using vectors. So let's draw an argand diagram or a complex plane. And we're going to put about 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So the first one is z1 plus 1, so 4 minus I plus 1. So first I'm going to draw 4 minus I. That would be 4 to the right and 1 down. Be right there, right? And then plus 1 would be 1 to the right. Okay, and then we're going to add those two together. It'll give us 5 minus I. Okay, so the brown one is 5 minus I, 5 to the right and 1 down, right? So we've also found the result just by drawing the vectors. Z2 plus 1/2 Z1. So Z2 would be 2 plus 3I, so that would be 2 plus 3I would be about like that. Okay, let me try that again. 2 plus 3I would be about like that. 2 plus 3I. And then I'm going to add 2 minus 0.5I. 2 minus 0.5I would be 2 to the right and 0.5 down. Okay? So that would be down. So the resultant vector here would be 4 plus 2.5I. So it would be, okay, it would be that. All right, so we found the answers both by adding vectors algebraically and also by using vectors. Show on an argand diagram 3 plus 2I and its conjugate, z conjugate equals 3 minus 2I. Okay, this is pretty easy. Okay, and then we're going to put maybe 3 slashes in each direction, because these are not big vectors. And first I'm going to draw 3 plus 2I, which would be 3 to the right and 2 up. Okay, that would be 3 plus 2I, and now I'm going to draw 3 minus 2I, which would be 3 to the right and 2 down. Like that, right? Okay, so there is the green original z, the z conjugate, z complex number, and z conjugate, which is its conjugate. It's just a reflection over the x-axis. With illustration why z minus z conjugate is always purely imaginary or zero. What distinguishes these two cases? Okay, so first of all, let's do a algebraic version. So let's say that z is a plus bi, and z conjugate is equal to a minus bi. Let's do z minus z conjugate. That would be a plus bi minus a minus bi, which would be equal to, like, a minus a cancels each other out. B plus b is going to be 2bi. Okay? So if we look at this, the a component is gone and the b component is doubled. So the only way that this could be anything but a purely imaginary number, because remember, b is a real number multiplied times I, which makes an imaginary. So b being real, this is like an imaginary number completely. The only way it wouldn't be is if b happens to be 0. So if b is 0, then the number z minus z conjugate is actually 2 times 0 times I, which is just 0. Okay? So what distinguishes these two cases is, in one case, the magnitude is 0, right? So let me draw that with an illustration. So let's see. We'll take the case of, let's say that Z is, well, we'll just draw it with A plus BI. So we'll say that Z is A plus BI. Okay, so it's A to the right and B up. And then I'm going to subtract the conjugate. And remember, the conjugate is a reflection that goes down, right? But if I'm going to subtract the conjugate, then instead of pointing this way, the conjugate is actually going to point this way, right? And if I wanted to subtract the conjugate, it's like adding the inverted direction conjugate. So I'm going to add the inverted direction conjugate. It's going to look kind of like that, right? So this is Z, and this is negative Z conjugate. And so do you see how when you add the two together, you're going to be somewhere on the y-axis. And the only way for this not to be a purely imaginary resultant vector, this vector here, is if the resultant vector happens to be 0. If the resultant vector is 0, then it wouldn't be imaginary at all, right? So like if Z was just like, if A plus BI, it was if the imaginary part was 0, then when you add Z and Z conjugate together, then are you going to subtract Z minus Z conjugate? It's just going to give you 0 for the real part and 0 for the imaginary part. Okay?